Hello everybody, my name is Geert Verdoolaege and I work at the Department of Applied Physics, Ghent University in Belgium, and also at the Laboratory for Plasma Physics of the Royal Military Academy in Belgium. So my talk is about pattern recognition in nuclear fusion data by means of geometric methods in probabilistic spaces. This is an overview of the talk. I will very briefly introduce the importance of stochastic uncertainty in fusion plasmas, and I will then come to the main topic of the talk, which is pattern recognition in probabilistic spaces. I will not, of course, discuss all of pattern recognition applications. I single out one, which is regression analysis, specifically a regression method, which we have been working on in my lab during several years now. It's a very robust and simple regression method called geodesic squares regression. And we then apply this first in fusion science to regress between properties of a very important plasma instability in fusion plasmas called edge localized modes. And then we also apply this in astronomy to a famous, very well-known scaling law called Tully-Fisher scaling. And then we conclude. Okay, so stochastic uncertainty in fusion plasmas. Of course, the reason I discuss fusion is because this is my main field of application, but many of the concepts and also techniques that I will be discussing can be applied also and are very relevant also in many other fields. So very briefly on fusion energy. So probably most of you are somewhat acquainted with this, and most of you probably know that fusion between light atomic nuclei is the power source for stars and our sun, and so fusion energy science is about building, so to speak, a star on Earth. And this would give us access to clean, safe, and virtually inexhaustible energy production. Now, the main and most developed route towards realizing this goal is a magnetic confinement fusion, and there are several types of devices in which this can be realized. One of them, and again the one that is most evolved, is the tokamak, and there are others, but the stellarator is also under development. So the main idea is to confine a hot hydrogen isotope gas, which is then basically becomes a plasma, which is a collection of charged and neutral particles, and we're going to confine this with a strong magnetic field. So that is the main principle. If the plasma becomes hot enough, the nuclei have sufficient energy at a certain point to start fusing, hence releasing energy. So this is presently culminating in what is called ITER, that is the next generation international tokamak, which is presently under construction in southern France. You see here on the left hand side a cut of a schematic of the ITER device, and so inside you have this torus shaped vacuum vessel wherein the plasma is generated. And so the size of this device is very large. On the right hand side you see the construction site, in a recent picture of the construction site, and so the main device is several stories in height, so it's a large scale and an international project. Now, a fusion plasma is a complex physical system, and actually the main one of the main challenges and difficulties in creating fusion is because the transport of heat and particles through this plasma occurs in a turbulent way. And understanding and controlling this turbulent transport is one of the main remaining issues towards realizing fusion energy. But there has been a lot of progress during the past few decades, and so as I said, this is culminating in the construction of ITER. Now, it's a very hostile environment to do measurements because it's of course a very hot plasma, difficult to probe, and hence there are a lot of uncertainties in the measurements, and so there are many different ways to do measurements at such a plasma, with many different types of sensors and diagnostics, but generally there's a lot of uncertainty that has to be dealt with, and that is not only a measurement uncertainty, but of course also uncertainty in the underlying models describing the diagnostics and describing also the underlying physics. And so it's a considerable challenge to deal with that uncertainty, and this is what this talk is actually about. So a few examples of uncertainty in fusion plasmas, or sources of uncertainty, and I'm basically actually going to discuss here statistical uncertainty. So sources of statistical uncertainty are of course on the one hand fluctuation at a microscopic scale of properties of the system, and one example is of course the turbulent transport of particles and energy, of which you see here a simulation, and another source of uncertainty is due to the measurement system, the diagnostics, the sensors, so measurement noise, let's call it that way. On the right hand side you see here an example that is relevant for the application that we are going to speak about in a minute. This is a picture actually of filaments in a fusion device called MAST. So these filaments are created by or generated by plasma instabilities and are expulsed from the plasma, and so this, since the filaments have a high energy, and this can be very dangerous or detrimental to the wall surrounding the plasma, and so this kind of instabilities have to be controlled. But so these are phenomena in a plasma that are inherently uncertain because they fluctuate, and the microscopic properties of those fluctuations are not well known. But at a different level one could also assign uncertainty, or there is uncertainty in any measurement that we do in a complex physical system. So this is here a graph of basically the confinement time, so that is a measure for the duration that the plasma particles stay together and have the opportunity to fuse, versus the density in the plasma. And these are measurements, so each point is a measurement from the fusion device JET, the largest fusion device up to date, and of the confinement time versus the density. Very difficult to see a specific pattern, the main reason being that there are also other variables that influence the confinement time. This is presently not the point here. What I want to indicate is that of course each of these measurements has uncertainty, and this is depicted here by an error bar that in this case represents a single standard deviation in the measurement of the plasma density, and also vertically in the measurement of the confinement time. So, and also this uncertainty is going to be due to, on the one hand, fluctuation of the system properties, but also measurement noise. Okay, so these are 3 examples. And now, having discussed this uncertainty, we're going to talk about data analysis, and specifically to do pattern recognition in probabilistic spaces which arise due to the uncertainty in the physical system. And we start very simply. I show here 2 points which might represent measurements. One of them might be a prediction due to a physical model. The other one might be a measurement, and you want to compare them. But the main point here is that if you want to do pattern recognition, if you want to find patterns in data, basically you're going to use distance measures between measurements and predictions, and so on. So the whole idea of a pattern, be it a cluster or a submanifold in a Euclidean data space, that whole idea of a pattern rests on the concept of distance between points. Now, of course, when we do a measurement, and this is what we just mentioned in the slides before, we realize that if we zoom in, actually that measurement is a sample from an underlying probability distribution. And if you would, for instance, do multiple measurements of the same quantity under some stationary macroscopic conditions, you would see that you always get slightly different measurements. So this is well known. This is what stochastic uncertainty is all about. But the important thing is that actually what appeared to be single measurement points or prediction and measurement point before, when you repeat the measurement, you will see that you actually have stochastic uncertainty there. And well, then of course when you want to do pattern recognition on such a data set, it would be an advantage to be able to, instead of measure the distance between the 2 points and try to find patterns from this kind of distances, Euclidean distances, it would be an advantage if we could actually employ that information that is in that underlying probability distribution. So, for instance, model that collection of repeated measurements by a probability distribution, and also here. So we model that by probability distribution, and then it would be good if we could measure the distance between those 2 underlying distributions. So one way to do that, and this is also what is well known in, for instance, in least squares, one way to do that is to look at each of the individual points. So you could be looking at individual measurement points on this side and individual predictions of those measurements on the other side. You're going to take the difference and take the sum of squares. And this is of course the principle of least squares. Slightly more involved, slightly more smarter is if you actually weigh the measurements by the measurement uncertainty, for instance by standard deviation. And this is then the basis for doing maximum likelihood to estimate parameters in a system or in a model, or maximum a posteriori, and if you are a Bayesian. So this is actually called the Mahalanobis distance between these 2 clusters, if you're going to estimate this kind of sum of squares. Now, the disadvantage here is that the Mahalanobis distance does not allow you to take into account the fact that this probability distribution, for instance of the observed, the measured points, might be different from the standard deviation of this predicted distribution. And if you are looking beyond Gaussian distributions, then higher order moments of the distribution might become important too, and might also be different from one distribution to another. So actually, we would need a measure, a distance measure between probability distributions that takes into account possibly the difference between higher order moments, starting with the second order moment, so the variance of or the standard deviation of the distribution. And there are various ways to do that in information theory to measure distances between probability distributions. And here we're going to take an approach which is rooted in a mathematical discipline that is quite well developed, called information geometry. And this will ultimately allow us to calculate distances between distributions. So what is the idea behind information geometry? The idea is that a family of probability distributions, and by family I mean one functional form of a PDF, for instance a Gaussian PDF, and the family is created by the parameters. So for instance the Gaussian family of probability distributions. Now this in information geometry is thought of as a differentiable manifold. So that is a well-known concept in differential geometry. So we could think about of this as a surface, if in 2 dimensions, a surface, curved surface, or a curved space in multiple dimensions. And in information geometry, the parameters of the probability distribution are going to be the coordinates on that differentiable manifold. For instance, the mean and the standard deviation form coordinates on the Gaussian family of probability distributions. And it turns out that there is a metric tensor, which is also a well-known concept from Riemannian differential geometry, a metric tensor that is actually the basis for calculating distances on such a manifold, and it is based on the Fisher information. Now the Fisher information is a well-known concept in statistics. I've written down here one of the formulas for calculating the Fisher information. So suppose that you have a parametric probability model, probability distribution of a certain quantity, might be a vector quantity x, depending on a number of parameters theta. And so theta is an m-dimensional parameter vector. Well, then the Fisher information is calculated through the second derivative with respect to the parameters of the log of that probability model. So that might be a log likelihood, and then we take the basically the expectation of that. That turns out to be valid, have the properties of a Riemannian metric tensor on the corresponding space of probability distributions, characterized by that parameter vector theta. And the line element, which is can be thought of intuitively as the infinitesimal distance between 2 points on that manifold, is calculated by this second order sum involving the coefficients, so the entries of the Fisher information of the metric tensor. So once you can do that, the whole machinery of Riemannian differential geometry becomes available and allows you to calculate from the metric tensor curves of minimum length between points on that manifold, and these are called geodesics. And if you calculate the length of such a curve, you actually have what is called a geodesic distance. Now this is in information geometry named after one of the originators of information geometry, Rao. And so this is called this shorter distance between probability distributions on a probabilistic manifold is called the Rao geodesic distance, and we're going to abbreviate this with GD. And so now we have a distance measure between probability distributions, and this is going to form the basis to do pattern recognition in probabilistic spaces. So pattern recognition, what does it involve? Basically classification, clustering. So classification is supervised, clustering is unsupervised. Regression analysis is yeah, of course, finding patterns at a certain macroscopic level between properties of a system. Dimensionality reduction is another task, and visualization is one result. If you do dimensionality reduction up to 3 or 2 dimensions, you can actually visualize data that actually lie in a higher dimensional space. So we have also turned an observation or a prediction from a single point, a structureless number, to a probability distribution. We realize that every point, every measurement that we take, every prediction that we make is uncertain and hence cannot be a single number, and has to be characterized instead by a distribution, a structured object. Of course, if you have access, the more, of course, you have access to the properties, the characteristics of that underlying distribution, the more information you have about the stochastic uncertainty. Now this information, as we will show, is important in doing pattern recognition between uncertain in spaces of uncertain data. Gives you more information, but we will also show that it gives you more flexibility in neglecting deviations from the underlying model. So we're going to measure distances between the probability distributions by the Rao geodesic distance, and I draw here the analogy between with measuring distances between objects or for instance animals, just to make intuitively clear that if we look at if we compare, for instance, a cat with a dog, we're not going to look at each of the individual microscopic characteristics. We're not going to measure, for instance, the length of the ears, the size of the ears, the size of the eyes, and so on and so on. We're not going to measure all that and then make the comparison. We're going to look intuitively at the animal as a whole and compare that with the other animal. So in the same vein, we do not want to compare individual points underlying, which might be samples of this distribution, with individual points of the other distribution. We want to, as the Rao geodesic distance allows us to do, we want to compare the probability distributions as objects as a whole. So this has all been relatively abstract up to now. So let's now focus on one of the measurement models or probability models that we encounter quite often, the most often in realistic data sets, which is the univariate Gaussian distribution. So the PDF is given by this expression, and this is actually a family of distributions characterized by their means and standard deviations. If you calculate the Fisher information from this probability model, you get this line element, providing you infinitesimal distances on the manifold of univariate Gaussian distributions. If you integrate that, it's going to give you geodesic distances. There are various ways to represent that manifold of Gaussian probability distributions, turns out that it actually forms what is called hyperbolic geometry, and there are various models that visualize that geometry in our two-dimensional Euclidean plane. The one on top is the Poincaré half plane, and what you actually see is a tiling of that plane where these half circles are actually geodesics between points on the hyperbolic plane. And if you want to draw the analogy with the univariate Gaussian distribution, then on the horizontal axis you have the mean, and on the vertical axis, which is only positive, of course, because you have the standard deviation, and standard deviation is always positive, so hence this is a half plane. So here you have each point in this plane represents a Gaussian probability distribution with the corresponding mean and standard deviation, and points lying on these curves are connected by geodesics represented by the curves. Now this is another model, it's called the Poincaré disk. This is actually a bounded model because you represent the whole of the hyperbolic geometry in this model, and also again here you see a tiling of that space. This is the Klein disk, another representation. So the great advantage also of using a univariate Gaussian measurement model is that it's going to give you an analytic geodesic distance. So there's a closed form expression for the geodesic distance between two Gaussian distributions. And I also still want to mention this YouTube video, which also gives some nice visualizations of the hyperbolic geometry. This is another model of hyperbolic geometry which I like because, well, it's a two-dimensional surface, and it can be embedded in our three-dimensional Euclidean space. So intuitively that gives you nicely that impression of a surface, a curved surface, which you can visualize in three-dimensional Euclidean space. Now it's only a partial model of the hyperbolic geometry, but it can serve to represent a number of Gaussian distributions. So again, so the model is called the pseudosphere or the tractroid in this case, and you have the mean of the probability, the Gaussian probability distribution in this circular direction, and you also see immediately, of course, that another limitation of the model is that it is periodic in the direction of the mean, and the standard deviation goes from a value of 1, and so you cannot go to lower standard deviation, hence it's only a partial representation of the hyperbolic plane, and standard deviation goes up in this direction. So again, points, and I've depicted here a few points on that manifold represent Gaussian distributions. For instance, here we have a Gaussian distribution with a mean of 4 and a standard deviation of 1.2. And here are a few other points, and I also depict the geodesics between these points. Now you see that the geodesics wind around the model, again, of course, because the model is periodic. Now sometimes this might be a bit confusing, and also for visualization purposes, what I sometimes do is to compress the model in the direction of the mean, and so to show so you see that it is compressed here, and so that you can actually depict the geodesics on one side of the surface, and it doesn't wind anymore around the surface. This is another visualization, again the same distributions on the pseudosphere, and now I'm going to compare with the model that I showed you also here, so the hyperbolic Poincaré half plane. So these are the same distributions. The points which you see here are the same distributions as the points that I've depicted here. Now the interesting thing is that, for instance, this point and this point, they have the same mean of 4. The mean is 4 of this distribution, but a different standard deviation. And similarly here, same mean, and you also see this here, but a different standard deviation. And here are the corresponding density functions drawn. So the pink one, or the magenta one, is this one. And you see that you have the cyan colored distribution has the same mean, but a larger standard deviation. And similarly here, the orange one and the purple one, same mean, but larger standard deviation. And well, what you actually also see here in the Poincaré half plane, but also on the pseudosphere, is that it turns out that the distributions with the larger standard deviations are actually closer together than the corresponding distributions with the same respective means, but with a smaller standard deviation. So these distributions are closer than these two. You also see that in the length of the geodesics, and intuitively this is clear because these distributions overlapped much more than these two distributions, and overlapping means that they predict much more similar state of knowledge, so that they contain a much more similar state of knowledge than these two distributions. Hence they are closer together if you measure their geodesic distance. And interestingly, if you would calculate the Euclidean distance between these distributions just by calculating the mean, the difference between their means, the difference between the standard deviations, and taking the sum of squares, you would actually see that the opposite. So these two distributions with a smaller standard deviation would be closer than these two, and this is not correct. So this does not take into account, the Euclidean distance does not take into account the underlying nature of the object between which we want to calculate the distance, namely the fact that these are probability distributions and not structureless points in a Euclidean space. Okay, then as an illustration also of this, I want to show you an illustration of the difference between Euclidean distance and geodesic distance between probability distributions. So you show you this example. So this is actually a visualization of a large database of measurements of energy confinement times in various fusion devices. Each of the colors actually represent a fusion device, one tokamak, and the points are measurements, individual measurements made in plasmas inside each of these tokamaks. And this database is used for several purposes, but what it actually can provide is the variation of the energy confinement time in each of these devices as a function of various other characteristics of the plasma, such as the plasma density, the electrical current through the plasma, the magnetic field strength which you use to confine the plasma, and so on. So that database gives you the confinement time with respect to a number of global plasma parameters. And it's a 9-dimensional database, so you have the confinement time and 8 global plasma parameters. So of course we cannot directly visualize this database because it's 9-dimensional. But what I've done here is to project the data points into the Euclidean plane, and hence then made a plot. And this has been done using multidimensional scaling, which is a technique that tries to preserve the interpoint distances So the pairwise distances between each pair of points tries to preserve that distance as much as possible compared to the respective distances in the original 9-dimensional space. Now here I've done this using the Euclidean distance in the original 9-dimensional space, and you try to preserve the Euclidean distance in the projected space. And here I've done this using the geodesic distance. So actually in the database also the error bars of each of the measurements are provided, and then each point actually gives you a mean, and the error bar gives you a standard deviation of a corresponding Gaussian distribution. So this is a very simple probabilistic representation of these data points. Now if you calculate again the geodesic distances between the Gaussian probability distributions and the original probabilistic manifold, and you then project this onto the Euclidean plane, this is the representation of the data which you will get. It looks quite different, and actually it's much easier to recognize interesting structure in clusters and submanifolds in this data representation. And that is why this projection, which takes into account the error bars on the data, is more useful to recognize structure or patterns in the data than the Euclidean representation. This is a more faithful representation which takes into account the uncertainty on each of those measured plasma parameters. So we have talked now about pattern recognition in probabilistic spaces, and let's now focus on one specific analysis task, which is regression. And this is going to turn out to be regression analysis in a probabilistic space, so it's an example of pattern recognition in probabilistic spaces. However, this is not going to be immediately clear, because this method, which we have called geodesically scarce regression, is actually a general purpose regression method. So it's useful for any regression analysis, and the great advantage is that it is extremely robust. And this is robust against for instance, outliers in the data, also uncertainty in the underlying model. And it's clear that in practical regression analysis problems, this can be very useful. And it will also turn out that the robustness is thanks to the fact that we take this probabilistic description of the data and then actually perform regression analysis on that probabilistic description. Okay, I briefly talk about a number of general challenges in regression analysis. Of course, there is uncertainty in the data. It could be measurement error, fluctuations in the system, but there is generally also model uncertainty. There could be variables that we haven't included into our description of the data, and which nevertheless influence the quantities that we want to predict with our regression analysis. There is of course always the choice between either a linear regression model or various choices of nonlinear models. Then the stochastic component of the regression model could be Gaussian, but might also be non-Gaussian. So these choices introduce model uncertainty. There can be heterogeneous data and also heterogeneous error bars. From one subset of the data could have different error bars from another subset. There can be uncertainty on both the response and predictor variables. So I denote the response variable here with y and predictor variables with xj. There could be atypical observations, better known as outliers. Near collinearity of the predictor variables can also introduce difficulties. And then also various transformations of the data can introduce further confusion or uncertainty. One very prominent example is when that occurs in many disciplines studying complex physical systems, including well, plasma physics, but also fluid dynamics, astronomy, geology, finance, and so on. One very prominent example is where people use power laws to model the dependence of a certain quantity on a number of predictor variables, and then take the logarithm on both sides, so to estimate the power law or the coefficients of the power law in this logarithmic space. So the advantage is that it then becomes, if we transform to this logarithmic space, this actually takes on the form of a linear regression problem. The disadvantage is that, of course, this is only exactly true if there would be no uncertainty on the underlying variable, on the variables. In reality, what happens if you take the log on both sides is that you're going to change the underlying probability distributions. For instance, if variables were characterized by a Gaussian distribution on the original scale, if you take the log, you're going to skew that distribution. And this introduces further difficulties into the analysis. And we're going to look at an example where this creates difficulties. Now, of course, we know that the workhorse for doing regression analysis in many fields of applications is still ordinary least squares, and this is primarily especially the case in application fields in the physical sciences that do not have a great tradition in a somewhat more advanced data analysis, and plasma physics is certainly one of them. Slightly more advanced is when you use maximum likelihood or maximum a posteriori to estimate the parameters of a model. This is an example here of a very simple linear regression model with one predictor variable and one response variable, and you assume that you have multiple measurements indexed by the letter I here. There are coefficients also of the regression model, the betas, which I summarize here by the vector theta. Now, suppose that you have a Gaussian measurement model for the response variable y, then in order to do maximum likelihood, you're going to also minimize basically this distance, but it is going to be weighted by the standard deviation of, so basically the uncertainty in the response variable. You're going to maximize this likelihood. So, and here, of course, again, we recognize the Mahalanobis distance. Now, in practice, in the vast majority of practical regression problems, this might be too simple. And of course, there exist in statistics and machine learning many methods that are much more advanced than these, but often in, especially again in those disciplines where data analysis is not very advanced, there is a certain people are a bit cautious to use more advanced methods, and there is a need definitely of a flexible and a robust regression method that is also very simple in its application. And this is what geodesic least squares is about. So again, here we see both in ordinary least squares and in maximum likelihood that parameter estimation comes down to distance minimization. You're going to minimize the distance between what you predict or what you expect according to your regression model and what you measure. This is depicted here for the case of ordinary least squares or maximum likelihood. So you minimize the distance, these distances on average between the measured points and the corresponding predictions. Now, this can be generalized in what is called the minimum distance approach, and this this goes into the direction of geodesic least squares. So minimum distance estimation is a class of methods for parameter estimation, and hence also, for instance, for regression analysis, in where you do not compare individual measurement points, but you're going to look at the distribution, the probability distribution that the model predicts versus the distribution that you actually observe from the data. And you're going to compare distances between those distributions. Now, for instance, in the Gaussian case, this allows you to compare not only the means of the distribution, but also the standard deviation. So you take into account the fact that not only the means of the predicted and observed distributions might be different, but also their standard deviations. And for other distributions, we could also look at higher order moments. A very popular distance measure or similarity measure between those distributions in minimum distance estimation is then the Hellinger divergence. And for the empirical distribution, the distribution that is suggested by the data, often a kernel density estimate is used. So geodesic least squares is similar to minimum distance estimation, but there are also important differences. Now I want to talk a bit more about what we have mentioned already here, the distribution that you predict and versus the distribution that you observe. So this is represented by this cartoon here. Again, a dependent variable y, predictor variable x. Suppose you have this linear regression model. The blue points are individual measurements. But then let's focus on a situation where you try to keep the underlying x fixed, and you could think of in a realistic case of keeping macroscopic conditions of the physical the physical system where you want to do predictions. You're going to take the macroscopic properties stationary, and so the only uncertainty that is still present in the measurements but also in the predictions is due to fluctuations of the underlying system and also measurement uncertainty. So that creates that stochastic uncertainty. So if we fix our macroscopic measurement conditions at this measurement site, stationary conditions, and we repeat predictions and we repeat measurements, this is the situation which we are going to get. So multiple predictions, but there is fluctuation, and multiple measurements and there is fluctuation. And similar to what we said here in minimum distance approach, we want to minimize the distance between the predicted distributions and the measured distributions. And in geodesic least squares terminology, we're going to use the terms modeled distribution and here the term observed distribution. So this is a very important picture, which is the basic forms the basics for geodesic least squares regression. So we want to minimize distances between those distributions instead of distances between individual points. And this is a very simple example that illustrates those concepts. So suppose you have a pipe with a fluid flow, a turbulent fluid flow through that pipe. And at a certain point there is a constriction, and as a result of that we know that on a macroscopic level the fluid velocity on average is going to increase from this cross-section into this cross-section. So there's an increase, a change of the velocity with a decrease of the cross-section of the pipe. That is a clear and of course very well known relationship between velocity and cross-section of the pipe. And so you could think in a very simple student experiment to let students measure fluid velocity at various locations along this pipe, and these locations correspond to what I've called here measurement sites. So you keep the macroscopic properties stationary, and so you keep the cross-section fixed, and you're going to measure average velocities. Now, of course, average velocities can only be inferred after you calculate, you measure velocities at various points inside the cross-section, and if you do this with respect to time, you're going to see that as on account of that turbulent flow, you're going to have fluctuation in the individual measurement points. And if you calculate the average of that, that gives you an average velocity at various points along that cross-section, so at various measurement sites. Again, at each measurement site you could have such a time trace, stochastic time trace of velocity versus time. It's mainly the velocity that in this case is stochastic, but in principle, if you go to sufficiently small scales, you would also see that the cross-section has a certain uncertainty, of course. Okay, so this is a very simple example of the regression problem between average fluid velocities and average cross-sections, whereas if we look at individual measurement size, we see that both of the quantities actually fluctuate. And so to do the regression, we don't want to compare average quantities, we actually want to compare the corresponding probability distributions. Now this then finally is the main idea behind geodesic least squares. This is a very simple example, again, where we have, we suppose we have a linear regression problem between a single response variable. We're going to take here the case of a univariate Gaussian distribution with a single response variable and a linear regression problem with a number of coefficients that are to be estimated and a number of predictor variables xj, and the index I again indexes the individual measurements. So of course you have multiple measurements, and then you're going to again, so this is the distribution that you would expect, the conditional distribution of this response variable conditional on the predictor variables that you would expect if your model, the stochastic component of the model and the functional form of the model, if those would be exactly correct also at the microscopic level. On the other hand, we also want to look with an unbiased eye, let's say, to the data and try to characterize the data taking into account as few assumptions as possible. And this is then going to be our observed distribution. This is the model distribution. We only are going to assume that the measurements are Gaussian, but with an unknown standard deviation. And then we want to minimize the distance between those distributions. Another important point to notice is here what the variance in the denominator here, which has been derived well, either using Gaussian error propagation or by marginalizing the true but unknown values of the predictor variables x. So this describes actually the total variance on the quantity that is on top here in the denominator, where the uncertainty on the predictor variables x has propagated through the regression model and contributes to the uncertainty on the response variable. Okay, so it's important to note that we allow both errors on the response and the predictor variables. So difference with minimum distance estimation, which I mentioned before, is that this is a very clearly a model-based approach. You use a certain model for the model distribution and a certain model for a Gaussian model for the observed distribution. And minimizing those raw geodesic distances is actually equivalent to regression on a probabilistic manifold. It is the equivalent of ordinary least squares on a Euclidean in a Euclidean space, where here we have to estimate, of course, the coefficients of the regression model and also this observed standard deviation that we assume to be unknown. And it is this standard deviation that introduces extra flexibility in the method. If we then have a number of data points and they are assumed to be IID, we can minimize the sum of square geodesic distances between modeled and observed distributions, and this actually is then what is geodesically square, so regression GLS. Again, it is the equivalent in a probabilistic space of ordinary least squares in a Euclidean space. And in fact, if you would force the modeled standard deviation, because this is actually the model standard deviation, if we would force this to be equal to the observed standard deviation, then that raw geodesic distance between those two distributions would reduce to the Mahalanobis distance, and you would actually just get maximum likelihood. So that is a special case if these two if the standard deviations are forced to be the same. In geodesic least squares, the standard deviation of the model distribution and observed distribution can be different. And again, if we would look at other distributions than the Gaussian distributions, you could also be looking at differences between higher order moments. The raw geodesic distance takes this all into account by looking at the probability distributions as individual objects and calculating the distance or the difference between those objects as a whole. Okay, so we now come to our first application of geodesic least squares regression in fusion science about edge localized plasma instabilities. So an edge localized plasma instability, or an edge localized modes as it is commonly known in fusion science, an ELM, is a repetitive instability in the plasma edge. It has a magnetohydrodynamic origin, and this is a picture I already showed. So it causes expulsion of plasma energy and particles in a brief burst of a few milliseconds each, and the energy and the particles are concentrated along these filaments which follow the magnetic field lines. There is a certain analogy, also due to taking into account the magnetohydrodynamic origin, with solar flares, and also a more down-to-earth analogy that I'm showing here of a cooking pot, where if you put a lid on a pot with boiling water, and the pressure builds up, it's going to be sufficiently strong to temporarily lift the lid, hence creating a channel to release some pressure. And this is a periodic phenomenon, so you're going to have this trembling of the lid, periodic movement of the lid, and this is actually at least as in a few superficial respects similar to edge localized modes in fusion plasmas. So there are various reasons why ELMs are important, an important topic in fusion science. One of them being, of course, that due to the loss of plasma particles and energy from the plasma caused by an ELM, there is a certain degradation of the confinement of the plasma. Even more important are potential damaging effects, where large ELMs could be dangerous for the integrity of wall components facing the plasma in next generation fusion devices. On the other hand, there is also somewhat a beneficial effect in that the elms might help in flushing impurities, which are heavier ions, heavier than the hydrogen, flushing these impurities from the plasma, which otherwise lead to a degraded performance of the plasma. Here on the right I've shown there's a snapshot from a discharge, a plasma discharge in the JET device. Actually what is shown here is a spectroscopic signal from beryllium-2, which is used as a diagnostic to detect elms. So you see here a very brief time trace. The peaks are due to the elms and are caused by the plasma interacting with the wall components, some of which are made of beryllium, and hence lead to excitation of beryllium atoms near the periphery of the plasma and cause a spike in the spectroscopic signal. So you see that it only takes a few milliseconds for an elm to occur, and it's a periodic event. So typically in a single discharge, in a high confinement mode, in JET, you could have tens to hundreds of elms. So the important effects of elms lead to a field in fusion technology which is about controlling the elms or even mitigating them. So one of the approaches is to increase the frequency with which the elms occurs, because it has been observed that for this type of elms the energy released by the elm is inversely proportional to the frequency. So if you find a way to actually increase that frequency, and there are various ways, then you could decrease the energy per elm. So that is elm control. Okay, so let's now zoom into a few properties of the elms in the JET device. So we looked at 32 recent JET discharges, plasma discharges, each of them containing many elms, many elm events, and we're going to look at a few characteristics of the elms. And the first characteristic we look into is what we call here the waiting time, which is for a specific elm simply the time since the previous elm. So you could for instance look at the time between the starting points of the elms or the peak points of the elms. Those gives you a handle on the time between each individual pair of elms. Okay, so we're going to measure that time for each pair of elms in each of these 32 discharges. And then the second quantity that we are going to look at is the energy that is typically carried from the plasma by an individual elm. And one way to look at to measure that energy is by looking at a magnetic signal that gives you an estimate of the stored energy in the plasma. And if you look at that signal when an elm occurs, so here you have again that spectroscopic signal, you see that there is a drop in the stored energy, the total stored energy in the plasma, which is due to the elm, of course, carrying some of the energy of the plasma outside, out of the plasma. And for each elm, we're going to measure how large that drop of energy is. Okay, so we have the time between elms, and we have the drop of energy of the elms. Now let's see how these two are correlated. And indeed, if you plot for each of the 32 discharges, so the 32 points here in this plot, you plot the average elm energy loss versus the average time since the previous elm, you're going to get a graph like this. So once again, each point here represents the average over all the elms in the corresponding discharge, the average of the waiting time between elms, and the average energy of the elms. And you see that indeed on average there is a clear, perhaps linear relation between energy and waiting time, at least in this range of measurements. Okay, so what you could then do is to do regression analysis, and to start do that, we are first going to look at the uncertainties, because we will need them if we want to do geodesic least squares regression on this data set. Now the uncertainties that are depicted by the error bars here are actually standard deviations, because just of course as we can calculate averages of over all the elms in each of the discharges, we can also calculate those standard deviations. What are depicted here are actually the standard deviations on the average quantities. So for each discharge we still have to divide the standard deviation of the probability distribution by the square root of the number of elms in each discharge, and those give these error bars here. You also see that the error bars appear to be proportional to the measurements, so the averages themselves. So there are heterogeneous, there is heteroskedasticity here, heterogeneous error bars. And this is then the regression analysis. The regression analysis on these average quantities, which we can do with ordinary least squares. That is the green line here. And so I've just taken a very simple linear relation between elm energy and waiting time. And I've taken proportional error bars, but of course the error bars are not used in ordinary least squares, and you see that, so that the result is this green line. Now if we use maximum a posteriori, and we get this blue line, which is quite different. The slope is quite a bit lower than what you get in ordinary least squares. Maximum a posteriori takes into account the heteroskedasticity, the fact that the error bars are different from one measurement to another, and here we have taken them to be proportional to the average measurements. And then finally there is geodesic least squares, which is going to calculate the raw geodesic distance between those measured Gaussian distributions. We take the distributions here to be Gaussian, and predicted distribution predicted when each of the assumptions underlying the regression model would be exactly true. You see that again there is somewhat a difference. Now, of course, it's very difficult at this point to judge which estimate is the best. Provisionally, we could say that it makes sense to trust less those points here, which have a much higher, a larger error bar, than the points here at the bottom, which have a smaller error bar. So in this sense, it could indeed be sensible to decrease the slope up to the values more or less estimated by maximum a posteriori and geodesic least squares. And here you see, I just wanted to show you also what it gives you on the pseudosphere, on the tractoroid. If you plot the data, so again you have the mean in this direction, standard deviation in this direction. This is the plot. The blue points are the data points. And for the dependent variable, so for the energy released by the elms, and the green points are the modeled points, modeled by the regression model. And so on the pseudosphere, we're going to minimize the geodesic distances between each of those respective points. This is a projection, again obtained by multidimensional scaling. Again, the blue points are the data points. The mean runs more or less in this direction, so you recognize this shape of the underlying manifold. And the standard deviation basically goes more or less in this direction, in the perpendicular direction. blue points are the data points. The dark green points, or the dark connected by the dark green line, are the modeled probability distributions, and the light green line here are the observed probability distributions. So in this projection, it's relatively clear to see that the observed standard deviation is quite a bit higher than both the modeled standard deviation and the standard deviation suggested by the measurements. Once again, because the standard deviation increases in this direction. So that observed standard deviation is quite a bit higher, and the reason is that the geodesic least squares takes into account the possibility that the points here on top might actually have in reality a larger uncertainty than what is suggested by the standard deviations that we have calculated from the data. And the advantage is that if you assume that in reality the uncertainty on these points is actually larger, then you are able to lower the slope of the estimated regression line, and hence better take into account the relative uncertainty of these points versus the uncertainty on these points. And that is why that estimated observed standard deviation is larger than the calculated standard deviation. Now the picture is quite different if we look at the individual measurements for each single elm in the whole data set. So for the 32 discharges, we look at the measurements of energy released by each elm and time since the previous elm for each elm in all those discharges. And if we plot that, we get a much more noisy pattern. So whereas between the average quantities there was quite a nice linear relation, the pattern is quite different here. So you see again, as you go to higher waiting times and higher energy, the spread on the distribution becomes larger, and it's actually becoming quite different to see that pattern between those two quantities. So what happens if we do regression analysis on this data set? By the way, these the magenta points are the averages, and so the blue points are the measurements for each individual elm. So what happens if we do regression analysis? I actually here mention the regression estimates for the coefficients, so the cutoff and the slope of the regression line. And this is for the case of the average quantities, which I just showed before. I've mentioned here the results of ordinary least squares and geodesic least squares. I'm not going to focus on the cutoff. We're rather, and this is also of more practical importance, we're rather going to look at the slope. And so you see here a certain estimate. And let's now do the same exercise if we look at the individual elms. So on the blue points, we're going to do regression analysis between energy and waiting time. With ordinary least squares, we get a totally different value, because that doesn't take into account the error bars. With geodesic least squares for the slope, we get a relatively similar value. So what you see here in the plot are the resulting regression lines, if in each case we assume a linear regression model. With ordinary least squares, we had a relatively large slope for the average quantities, much lower slope for the individual quantities. With geodesic least squares, the two red lines, we have a relatively good correspondence. The blue lines are for maximum a posteriori, not indicated here, but you also see that the slope is quite different in the two cases. So it turns out that geodesic least squares gives us much more consistent results between the average and the individual quantities. Okay, and then finally we go to our second application in astronomy, This is about a very important scaling law in astronomy called the baryonic-Tully-Fisher relation. And it's a very simple and very tight relation for disk galaxies between the total baryonic mass in the galaxy and the rotational velocity measured at a certain point in the rotation curve. So there turns out to be a power law relation between these two quantities, and of course if you do regression analysis for a specific data set, the goal is going to be to estimate this beta naught and beta 1. Various purposes for this scaling law. It can be used as a distance indicator, which is a very important task in astronomy, sets constraints on galaxy formation models, and can also be used as a test for alternatives to the prevailing lambda cold dark matter cosmological model. Specifically the slope, characterized here by beta 1, or the exponent here, and the scatter around the scaling law are important in order to evaluate alternatives to lambda CDM. So, simple experiment. We take data from 47 gas-rich galaxies, and we're going to do the following test. So, we have a power law relation here. Well, in the beginning I mentioned that it is extremely common practice to take the logarithm on both sides and then to assume that this becomes a linear regression problem. So we're going to do this on the log linear scale, where we assume that the standard deviation, observed standard deviation on the measurements is parameterized by this parameter S ops, which is assumed to be the same on the logarithmic scale for all measurements. That means if you do nonlinear regression on the original scale, you actually assume that the observed standard deviation is proportional to the measurements of the response variable, and that is then parameterized by this parameter R ops. So proportional on the original scale, that means a fixed uncertainty on the logarithmic scale. And this is quite, if you look at the data, this is quite sensible to, just as we did in the example on ELMS, to assume that the standard deviation is proportional to the measurements of the response variable. And then we're going to do the regression analysis on the log linear scale, nonlinear scale, with several methods. So we're going to do this benchmarking test, ordinary least squares. We also here use not maximum a posteriori, but also Bayesian method that takes into account errors in all variables, predictor and response variables, and where the standard deviations are marginalized. That means that it's also a robust method. So we marginalize standard deviations from the model. That means that it becomes also a robust method. So this we're going to refer to as the Bayes method. Geodesic least squares, GLS, and then also by way of a test we're going to replace the raw geodesic distance between the observed and predicted distributions, observed and model distributions. We're going to replace the raw geodesic distance by the Kullback-Leibler divergence. Very well-known similarity measure in information theory. So these two methods are actually the same except for the distance measure. Okay? So as promised, we first do the regression analysis on the logarithmic scale between masses and rotation velocities. Here we assume with geodesic least squares that the error bars are the same on each of the measurements. You see that because these are experimental error bars, it's not exactly fulfilled, but we will also see that geodesic least squares is able to cope with that thanks to its flexibility. And of course ordinary least squares, which is the method that is in many cases used to estimate this kind of scaling laws, does not even take into account the error bars. So we see that the various methods seem to agree relatively well on the estimates. But now comes a bit of a surprise, because if we do the same analysis on the original scale, so this is a nonlinear regression using the power law of the Tully-Fisher scaling, we get quite a different picture. Specifically, there seem to be a number of points, especially this one, that could be characterized as outliers, and we also see that ordinary least squares is heavily attracted to those points. On the other hand, the methods, the robust methods that do take into account the error bars on the data, are not fooled by these points. They take into account the fact that these have clearly larger error bars, specifically on the mass, for the larger masses, and hence they assign a lower weight to these measurements and are not attracted by the corresponding measurements. So this is the result actually of a bootstrap analysis, where we have replicated the same data set, resampled data set many times, and in each occasion have done the regression analysis using each of the methods, and then what we plot here is a histogram of the slope parameter in each of these regression analysis on the many times resampled data set. So you see that in the this is in the log linear case, there is a relatively good correspondence between those histograms, but if you look on the nonlinear scale, you see that ordinary least squares is all over the place in with the estimate of the slope parameter, whereas the robust methods are much more in correspondence. Finally, what you also see is that if you look at the observed standard deviation, which is here plotted, so the observed standard deviation is on the response variable always, and we plot this versus the measurement of the masses of the response variables themselves. Well, in the we assume that they are proportional, error bar proportional to the measurement itself on the original scale. You see that the estimate of the observed standard deviation is quite a bit higher than both on average the modeled standard deviations and also the standard deviations that are actually given by the experimentalists. This is of course on a log-log scale, so the difference is quite large. Actually, on average, the relative error on the masses is 38% over the whole data set for the experimental values, and 63%, so much higher, for the estimated observed standard deviation. And again, as we have seen for the example in the case of the elms, this is this explains how geodesic least squares can ignore these points with a higher standard deviation. So it is going to increase the observed standard deviation up to the point where it is able to take into account these deviations. This is going to lead to this higher observed standard deviations. Put in other words, the method recognizes that the true, taken over the whole dataset, the true standard deviation or uncertainty is actually quite a bit higher on the nonlinear scale than what was suggested by the measurement errors alone. And this is the same picture on the pseudosphere. Again, you will see that each of the points here, the red points correspond to observed standard deviation, are displaced in the upwards direction. That means to a direction of higher standard deviation compared to the blue points, which are the experimental data points. Okay, and then we're going to conclude. So probabilistic modeling of properties, stochastic properties in a complex physical system is of course important, and it is especially important if we're going to do pattern recognition, for instance regression analysis, but also classification or clustering on data sets with a lot of stochastic uncertainty. We have used here information geometry as a mathematical tool that provides us a means to calculate distances between probability distributions. The advantage being that we have this geometrical intuition, which we have here illustrated by means of the pseudosphere. By the way, I also want to mention that with other distance measures such as the Kullback-Leibler or Hellinger divergence, the disadvantage is that you do not have this geometrical intuition. So this is given that distance measure, this allowed us to do pattern recognition in probabilistic spaces, and we have seen that this extra information that is provided by the probability distributions of fluctuating system properties provide us with more information that is going to be important and is going to give us more flexibility in estimating structures, patterns in the data. And we have here focused on geodesic least squares regression as a flexible and a robust method to do regression analysis on such data. The other extremely important advantage is that it is an easy to use and also a fast method, and especially the fact that it is an easy method that copes with a lot of issues in regression analysis for general purpose regression in practical applications. It copes with all these issues and nevertheless is still easy to use. Well, that is a combination that is relatively unique in regression analysis, and hence the hope is that our method of geodesic least squares is going to be used more by also practitioners in the field as a much more robust alternative to ordinary least squares for important regression problems. Thank you very much.